Hello physics students. Welcome to Spark Lab 1, Uniform Velocity. Now at this point, you should have already printed out pages 3 and 4 of the sheets of the document I included in our Google Stream. Pages 1 and 2 are instructions. You're welcome to print those out if you find that convenient, but you don't have to, okay? You could just use those on the screen. But the lab sheet, of course, you have to write on that, and that's what you're going to submit, so that's what you need to print out. All right, so in this experiment, this is the goal. These are the goals, the learning goals. You will learn the shapes of the distance versus time graph and velocity versus time graphs for an object with uniform velocity. You're going to learn the slope of a displacement versus time graph is equal to the velocity of the object, and the slope of a velocity versus time graph is equal to the acceleration of an object. All for uniform velocity. You're going to learn all about the graphs of such an object. And what we're going to use to achieve these goals is something called a spark timer, 2 pieces of spark tape on this roll, about 30 centimeters long, 1 for each lab partner, a ruler or meter stick, and an electric car. This little dune buggy is what's going to go at a constant velocity across this table, and then we're going to analyze that with the spark timer. Now, what exactly is a spark timer? Well, let me bring it closer to the camera so you can see. So it's this device that when I turn this switch on, it creates sparks, which you can't hear until I put paper in there, between the metal prongs here and the plastic underneath. You can't touch it because it's protected by plastic, so you can't get electrocuted. And when that electricity passes over here, it's going to hit some spark tape, special paper that leaves marks whenever electricity passes through it. So what I'm going to do is I'm just going to make a quick spark tape so you could see how that's going to allow us to analyze the motion of an object in Spark Lab 1 and Spark Lab 2. I'm going to feed this spark tape, special paper, through the spark timer in the direction of the arrow. What I'm going to do is I'm going to turn the timer on, and I'm going to pull the tape first slowly, and then I'm going to pull rapidly, and we'll see what happens to the pattern of the sparks. So, okay, slow, and then fast, okay? Now this may be a little hard to see. Maybe I'll get a little white background here. But what you should see here in the beginning is that the spark marks are very close together. And then when I pulled the tape faster, the spark marks were farther apart. Why? Well, the spark timer, it creates sparks at a constant rate of 60 sparks in 1 second. Very fast, okay? That means from one spark to the next is 1/60th of a second. If you take your calculator and you do 1 divided by 60, you get 0.016 repeating. That's the time from one spark to the next. And whether I pull the tape fast or slow, the electronics don't know how fast the pace. It's just spark, 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 steady rate. So if you think about the formula, V equals distance divided by time. If time is always the same, because that's the spark timer, then when something goes faster, the numerator of V equals d over t has to change. And that means the distance from one spark to the next is greater for the same amount of time. So that's how it works and creates a record of the motion. So now what we're going to do is create a record of the motion of this little dune buggy. So I'll get a new piece of spark tape, about 30 centimeters long, and tear it off. And I'm going to attach it to the car, but I'm not going to attach it up high like this, because then what happens is the spark tape drags out like the hypotenuse of a triangle. So it won't match the speed of the car that way. What I have to do is attach it at approximately the same height on the card that it comes out of the timer. So like something like this, okay? There. And I'm ready to go. So I'm not reading the procedure because, you know, I know how it works, but basically now what I'm going to do is I'm going to turn the car on and hold it up so that the wheels spin, and it's kind of like in neutral right now. I'm going to turn the spark timer on and let the car go. So there it is, okay? So now we have spark tape, okay, which we need to analyze and interpret, which is the entire point of the lab. So in order to do that, let's switch to my desk cam view back at home. So I'll see you at home, I guess I could say.
Okay, welcome back, students. So remember, in the classroom we got ourselves a spark tape from the dune buggy car pulling the spark tape to the spark timer, and then in the procedure it instructed you to take a 15 centimeter long strip of this tape, cut it down, and put onto your lab sheet here. I've already done that for you. So what we're going to do, because this lab is being done remotely, is you're going to open a document that's 30-something pages long, and what's in that document are about 30 copies of this first sheet. And you're going to scroll down until you find the sheet with your name on it. Okay? I'm going to have your name written in here. You print out only that sheet for the first sheet of the lab. That'll ensure that everyone gets their own spark tape. Okay? So everyone will have their own data. Everyone's numbers all throughout this lab will be different. So you can certainly work with someone else in terms of figuring out what to do, but you should be calculating your own numbers, punching your own buttons on your own calculator, because everyone's data, everyone's spark tape will be different. Okay, so you'll have this already on the sheet you open, you print that out. Then you go back to the lab sheet and you don't print out this sheet because like I said, I have one with your name on it already, but the back with questions and spaces for answers, you have to go back to the original lab sheet and print that out. Everyone will have the same copy of this. It's blank page, and then you're going to answer the questions here. So now I'll take you through how to analyze this data. So we're up to essentially step 10 on this lab. So label the first dot on your spark tape 0, the next dot 1, the next dot 2, until you have 10 dots marked. And this diagram kind of shows you what I'm talking about there. I didn't write the word dot because there wasn't enough room, but you can certainly see I've numbered my dots 0 through 10. Okay? The next thing, step 11. Next, fill in the position column in your data sheet by measuring the total distance the car traveled at each interval. So if you look at this diagram, position 1 is the distance from dot 0 to dot 1. Position 2 is from 0 to 2. Position 3 is from 0 to 3. So what you're doing is you're measuring the total distance the car moved throughout the lab. What that means is you're going to put the ruler down one time, aligning it with dot 0, and then you're not going to move it for the rest of the lab. You're just going to measure off where each of these dots occur and fill in your data table. So let me show you that specifically on the spark tape. So what I'm doing is, as I said, I align my ruler with dot 0, which is about there. Now I'm going to try and zoom in here and see if we could get a better view. Okay, let's try maybe. Okay, so there's the alignment with dot 0. Dot 1 you can see right there. Now this is important in this lab, how to use a ruler. You've probably heard it before, but the ruler, some people might quickly say this is 0.7 centimeters, which is right here, right? This is 1 centimeter, 0.7 is right there. But if you notice, the dot is not exactly on that line. It's a little bit beyond it. So the correct way to use a ruler is to estimate how far beyond the 0.7 line that dot is. I would say maybe 0.7, it's not in the middle, which would be 0.75. It's a little bit to the left. I would say maybe it's 0.73 centimeters, that dot right there. Now, some people might say, I think it's 0.72, okay? Other people might say, well, actually, I think it is 0.75. Again, that's an estimate. So we can all disagree on that, but we should not disagree that it's something beyond 0.7, but not beyond 0.8. So that's the estimate. I'm going to fill in the position over here for the first dot as 0.73, and I don't have to write the centimeters here because I have it already up here. So that unit applies to the entire column. Again, don't write this down because your spark tape will be different than mine. So your measurement will certainly be different. So let me zoom back out. Actually, you know what? Maybe I'll stay zoomed in a little bit longer. Read a couple more points. So 0.73. The next one, well, if you look, this dot is greater than 1.4, but less than 1.5. To me, it looks like it's right in the middle. So maybe I'll call this one 1.45 centimeters. And I'm jotting that down in the data table. The third dot, which is right here, if you look, it's 2.2, between 2.1 and 2.2, almost, it's closer to 2.2. So I would say maybe like 2.18, maybe. 2.18. I'll jot that down in my data table. Okay. And then the fourth dot. Okay. That looks to me like it's exactly on the 2.9. So I don't write 2.9. I write 2.90. Okay, 2.90. That indicates to someone reading the data that that last zero is an estimate, and maybe it's not right on the line. Maybe it's 2.91 in reality, or 2.89. Again, that zero at the end does mean something. Oh, it doesn't matter. 2.9, 2.90, the same thing. Well, in math, when we're dealing with numbers in theory, that's true. But in measurement in science, there is a difference between 2.9 and 2.90. 2.90 is more precise, we say. We say that it tells the person reading that the measurement tool went to the 10th place and the last zero was an estimate. Okay, so it is actually critical. All right, what I'm going to do is pause the video and I'll just show you the results of the rest of my readings because you don't need to follow me with the measurements through all my measurements. All right, so here are all my measurements. Again, you're not writing these down. You will have your own numbers that should be different than everyone else in the class because everyone will have their own spark tape. And then the other thing is that what should be similar for you is that you should have two numbers after the decimal for all of your measurements. Okay. Now, the next thing we want to do is step 12. Step 12 says, from the values in your data table, calculate the change in position, delta P, of the car, which will be the distance between each pair of successive dots. Now, what we could do is we could go back and measure this, measure that, measure that, measure that, and put in all the numbers here. And notice we get about the same for every delta P. Maybe it's like 0.6 centimeters for each one of these because the spacing is the same. So these numbers should be all approximately constant, but they should be based on the measurements. But rather than going back and remeasuring again, we could use these numbers. And what we could do is take the total distance, say we want the distance between dots 2 and 3. We could take the total distance from 0 to 3 and subtract off the distance from 0 to 2, and that will be the distance from 2 to 3. In other words, we could take these two numbers and subtract them, put them here. That would be the space between dots 2 and 3. So that's what we're going to do here. For this column, we're going to subtract each pair of adjacent points. The first one, we're doing 0.73 minus 0, which we don't even need to put on the calculator. We could just put 0.73. Again, no need to put the unit here because it's up at the top. That applies to the whole column. Here, we could do 1.45, this number, subtract 0.73, and I get 0.72. Then, for this, I subtract these two numbers right here, 2.18, subtract 1.45, and I get 0.73. Then I'm going to subtract 2.9 and 2.18, these two numbers, and I get 0.72. I'm going to subtract these two. And I get 0.72. Okay, so I'll pause. I'll go ahead and do the rest. You don't need to watch me, but you're going to do the rest on your own lab sheet for your own data. So there are the rest of my values filled into my data table. Now we're going to move on to this column, and that is step 13 of the lab instructions. It says from the delta P column, calculate the average speed of the car between each pair of dots. When calculating, think carefully about what the time is between each pair of dots. So what I'm going to do is figure out the speed in all these intervals. For example, let's suppose I want to find the speed between dots 3 and 4. What I have to do is I have to use the formula for speed. So that is, lost the focus here, okay, from the reference table, speed is distance over time. What I need is the distance between each pair of dots and the time between each pair of dots. Now the distance between dots 3 and 4, I could get out a ruler and measure that, but there's no need for that because I have that right here. The distance between dots 3 and 4 is 0.72. So that's what I put in for my distance right there, 0.72. That's centimeters. By the way, we're staying in centimeters, as you could see from this lab. We're just sticking with centimeters and centimeters a second. It makes things more convenient for this lab instead of using meters. Okay, now the next thing I need is the time between dots 3 and 4. And some people might go over here for the time and say it's 4/60ths of a second, or maybe 3. Not so. What I want the time is from this spark to that spark. And it's neither of these. The time from one spark to the next with the spark timer is always 1/60th of a second. So that's what I plug in to get the speed using that displacement. So what I'm going to do is just take my calculator and do 0.72 divided by, and what I need with this style calculator is some parentheses. I think the TI-84 makes it all in the denominator anyway, so you don't need those parentheses on the 84. I hit enter and I get 43.2. So 43.2, and the units again are there. So that's what I do to all of these. I divide all of these, which are the distances between each set of dots, by always 1/60. So for example, I do 0.73 divided by 1/60, and I get 43.8. That goes here. Now what I would recommend is, because many of these are repeated, go down and look for every 0.73 and fill in the 43.8. You don't have to calculate over and over again, right? We already know what that is. And then for every 0.72, put in 43.2. Oops. And then I have 0.71, 42.6, 42.6, and then the 0.7. You know what, I'll do this. 42. So that's how the data table is filled. The next thing we have to do is we have to plot a couple graphs. So I'm going to go back to our procedure, our instructions here, and in step 14 it says position versus time. Plot the position versus time in the space provided on your analysis sheet. Then draw a straight line that best fits through the data points. Then calculate the slope of this line and then label the significance. So, position versus time. As you can see, we have time over here. That's going to go on the x-axis. It's already been set up for you. And then position is here. And that's on this axis. So our first data point is 0, 0. We can just go ahead and fill that in for 0 times 0 position. The next point is 1/60th of a second, 0.73. 1/60th of a second is right here. 0.73, well here's 1, 0.5, right in between is 0.75. So 0.73 is just a little bit below that halfway point. Then the next point is 1.45. So here's 2/60 of a second, 1.45. So 1.5 is there. 1.45 slightly below, maybe a little bit higher. Then 3/60ths, 2.18. So here's 3/60ths, 2.18. Well, here's 2, 2.5, 2.25. 2.18, so a little bit below that. So we just go ahead and plot all these points, and I'm just going to pause the video, do that, and then we'll look at the result for the next part of the procedure. I've plotted all my points, which was 14A. Now 14B says draw a straight line that best fits through the data points. So what I'm going to do is, first of all, I need a straight edge, like a ruler, and so don't draw this freehand, you're going to lose points. The next thing that I have to do is I have to find a place where the ruler goes through the center of the trend, and actually the points are pretty much right on the ruler, so for me it's pretty easy to draw a best fit line. But like I said, what I would recommend to students is that once you do this, you go and you dot your points in ink. So I'm using purple ink, but the reason why I do this is in case I mess up and I want to erase the best fit line, I could erase aggressively, get the line out of there, and the points will stay behind. So I think that's a good idea, you know, in case you have to do a little trial and error with a best fit line. Always tricky for students. For example, if someone drew a line like this, all right, so that would lose points because yes, you have half the points above and half and below, but it's not following the trend, right? These points are clearly steeper than that line. So look, so what I could do here is just go like that, and my data points stayed because I dotted them in ink. So obviously what I want is a line something like this, and there. Let's see how that comes out. Oops, I moved it. All right. And that pretty much goes through all the points. So it's a good best fit line. There's one a little bit above here, one a little bit below there. So, you know, pretty good. Okay, so I'm going to stick with that. So the next thing that I have to do is calculate the slope of this line. And I've said this before in the Pi Lab and in the lesson about calculating slopes. You never use data points. Some people might say, well, why don't I use this and this number? Okay, but data points are not used because the best fit line is like an average. And let's suppose you wanted to find the average height of a Clarkstown student. If you average everyone, or the height of a Clarkstown, you average everyone, that's better than taking the height of one student and saying, oh, that's the height of a Clarkstown student. When you do the slope of these 2 points, you're basically saying these 2 points are all that matter, and all the ones in between do not matter. So that's why we do not use data points. Technically, you could use them if they're on the best fit line, but I just recommend staying away from them. The other thing you don't want to do is do the slope by making a little triangle like this. Too small. It makes your result imprecise. What you want to do is use as much of the line as possible. In fact, the whole line, or even more than the data point line, I would go right here and see this, and 0, 0, I would pick those points. Okay? Now I could say, I write slope equals change in y over change in x, or you could put delta p over delta t, okay? But anyways, an equation, we need that always in the Regents. Then what I'm going to do is I'm going to take the y values, go up to looks like 7.9 maybe. That's a little bit less than 8. So for me, again, your calculation here is going to be different because you're going to have different data and a different best fit line. But for me, I'm going to say 7.9 centimeters. And then the other data point is 0 centimeters, the origin, because my line goes through the origin. Then I'm going to divide by the time, the delta p. The final time was 11 over 60, and the initial time was 0. And you could put seconds there also. Now, you got to be careful when you enter this. You're going to need parentheses. So what I'm going to say is, let's clear this out, parentheses 7.9 minus 0, and the parentheses, divided by 11 divided by 60 minus 0, there, 43.1 maybe I'll say. Okay, so 43.1. Now, every answer needs units unless they cancel, like they did in the Pi Lab. If I had centimeters on top and centimeters on the bottom, there'd be no units, but I don't. I have centimeters on top and I have seconds on the bottom, which means the units are centimeters per second. Okay, so that is the result there. And finally, I'm not going to help you with 14D other than to say one hint. So label the significance of this value, this right here. What kinematic quantity does it represent? Hint, study the units. So notice it's centimeters per second. What is centimeters per second in this unit a measure of? Put it here. It's something that we studied out of the terms in the first video of this unit, that long video with the kinematic definitions. It's one of those terms belongs here. Okay? Now, 15, what I'm going to do is plot the speed versus time in the space provided on your analysis sheet, and then draw a line that best fits through the data. So the speed is over here in this column, and the time is over here. So I'm going to plot these two. Now notice they don't line up perfectly. Whether you call this 0 or 1, or some people even say 0.5 over 60 because it's right in between, it doesn't matter. As long as you go with this time and these here plotted on this graph. So what I'm going to do is I'm going to pause and I'm just going to go ahead and plot, well, maybe I'll do one. So like for example, 0, 43.8. So 40, these are obviously increments of 2, 42, 44, 46, 48, 50. So 43.8, well, here's 44, right? 42, 44. 43.8 is a little bit below that. Maybe what I'm going to do is I'm going to put that at 0.5 over 60 right here, right in between. My second one is 43.2. So here's at, and then also, sorry for all the movement, 43.2, that's between 1 and 2/60ths of a second. So between 1 and 2/60 of the second, it's going to plot right here. And I'm going to go up to 43.2. So here's 42, 44, 43 is right between, and 43.2 is a little bit above, so something like that. The next one, 43.8 on the data table. I won't move, but 43.8 would be somewhere around there. So I'm going to go ahead and plot those, and I'll start the video again after I'm done. All right, so those are the data points plotted. And now I'm up to 15b. Draw a line that best fits through the data points. Hint, the speed is constant. How do you plot a graph of something that remains constant? So if I draw a best fit line there, am I going like this or like this? No, this is an increasing speed. This is a decreasing speed. How do I draw a constant speed? Like that, right? So I need to draw a line that goes through the data points that's horizontal. So once again, I am going to dot these in ink in case I need to erase. And then I won't erase away my points and have to start all over. So you probably don't see much of a difference there, but they are now in ink. So, all right, so I want to draw a horizontal line that kind of passes through the center of the trend, maybe something like this. Okay, not bad. You got a little bit of below here, maybe a little bit above. Maybe I could shift it down a little bit, but I think it's pretty close because we got a couple three that are barely above and one that's very far below. Those probably average out to being, offsetting. So there is the graph. From the rest of the lab, it's just questions. Like, for example, look at your spark tape. How can you tell a car moves at a constant speed? Make sure to explain thoroughly. It is not enough to say the dots are equally spaced. Here's a hint. Write down the formula that defines speed and then dissect it. So many students just don't do that. So the way you would answer that is, let me see. Oh, here's the second page. Number one, write down, maybe I'll leave my hand here, it might help with the focus. Since V equals D over, see, it says hint, write down the formula. Everyone should start with this. Now, the rest of the question, think about this is constant. On this side of the formula, how can this remain constant based on these two variables? And think about the spacing of the tape. Talk about this and this for each pair of marks on the spark tape. Both things, okay? That's number one. That would be the complete explanation. The other thing I want to say is about step 3 and 4. It says sketch what ideal distance versus time, velocity versus time, and acceleration versus time look like for a car moving at a constant speed. Make 3 graphs. Sketch means that you're not actually plotting any data. Simply draw a line that illustrates what the graphs look like. 2 of the graphs, you can go back to page 1 and see what they look like. So sketch in here. Then think about this, what it should be for a car with a constant speed. How do you graph that acceleration? And then finally, step 4, On the same graphs you generated to answer the previous question, sketch the graphs for an object moving with half the speed. Label these plots clearly, like car with half speed, or you could even just write half speed next to the plots. So you're going to have 3 graphs here. On the same graphs, you're sketching the plots with half speed, and you're writing the words half speed next to those plots, so I know which is which. So that's the Spark Lab 1 uniform velocity. So I hope everything goes well for you. Remember, you have your own Spark tape, your own data, your own graph. Everyone's going to have their own data, own graphs, own slope calculation. Make sure you're punching your own buttons on your calculator to get all your results. So that's it. Good luck with the rest of the lab. I'll see you in the video for Spark Lab 2.